Alright, in this video I'm going to start implementing support for the VL6180 laser time of flight sensor. I have placed 4 of these sensors on this little board here, and I don't even know if they work yet. I don't even know if they are possibly shorted because they're very tiny sensors, and the package actually melts if you increase the temperature past 260 degrees. We'll see how many of them work, if they work at all. Let's get to it, and let's get started implementing this driver in C on STM32. Alright, so I've created a file here. It's going to be where I'm going to place all the driver code, and I'm going to expose this driver to the rest of the system as a generic analog device. With one channel, just giving the reading of the distance to whatever is in front of it. I may also add some console commands to this device driver just to make it easy to kind of read out the internal state of the sensor. So let's define a device driver and call it VL6180. VL6180, VL6180 probe, and VL6180 remove. Probe and remove are two methods that are going to be called. One is going to be called when the driver is initialized. The second one is going to be called when the driver is deinitialized. I'm going to include lib firmware driver and lib firmware analog, and we're going to create a static int VL6180 probe fdt node, return 0 there, and static int VL6180 probe, no, remove fdt node, and return -1 there because I'm not going to be implementing this method. In the probe method, I'm going to get I2C device, which is going to be, let's see. Actually, I have a few macros that I've defined for this other driver. Let's see here, where did I put them? Which I think I'm going to reuse. Actually, this macro. And I'm going to place this into driver header file. And this will provide kind of a generic way of getting the variables from the device tree and fetching them into the object, the local object for the device driver, the instance of the device driver. So let's see, what am I going to call this? Get ref, and this is going to be, let's see, actually, let's do like this. I wonder if this will work. So let's also then define this in the define device driver, declare Now, actually, I'm just going to supply that as a string. This concatenates the two strings there. So let's do like this. Main type ref. Maybe more like device ref. Okay, and device ref. And then VL6180. And we're gonna go. So I'm gonna define this struct as well. 6180 self is. Let's allocate this. This allocation is only done once during initialization, so when all the instances are allocated. Size of struct VL6180 and device ref VL6180, which here is going to be up. And I2C. VL6180 is going to have I2C device, I2C. So this macro is going to actually retrieve the reference from device tree, place it in the self I2C, and then print out the message if that failed. And now I want to initialize. I want to just see if I can get some kind of like a signature register which I can read in order to identify the device and make sure that I can actually communicate with the device. Let's see if there is such a register in this device. This is what it looks like. It has a laser transmitter and the receiver, and it's supposed to measure range from 0 to maybe slightly above 10 centimeters. And it does so by measuring the phase difference in light, I guess. So let's see here, which roughly translates to time of flight. Let's see where the description of the I2C interface is. Device registers. Identification 0 to 0F. Model ID. This looks like something we could read. Let's see. So, Interesting. This looks like a really unique identification number with date and time. Okay. So what is the I2C address that this actually talks about? Because it seems to me that this chip needs to there is like a chip enable pin, and it kind of looked like the chip enable pin is used to kind of select each chip and then read from it. So let's see. Kilohertz. Is there some description of the messages that you send to this device? So you can actually set the slave device address. Alright. Default 29. Okay. Looks good. So let's see if we can communicate with at least one of them. So and there's also going to be a GPIO device, which will hook up to the chip enable pin. And this will have int CE pin. So let's do like this. Zero by default, and now we should be able to do an I2C transfer to the. Let's see. So first of all, I'm going to add this to device tree, to my device tree for this particular board. And one of the important things here to think about is that I have to place the initialization of the GPIO pins before I initialize any of the devices, because if two of the devices are going to be enabled at the same time, for example, if the chip enable pin would end up being default high, which it by the way ends up being, then I won't be able to talk to any of these chips. So I have to do it like this. Let's see. Let's add it here. The first, the label in yellow is a label which is supposed to be unique across the whole device tree. That is also the unique name for this particular node, to which I can place references from other nodes. And the second text in green is the path to this node in the overall hierarchy of the device tree. So let's see here. Let's do this as an output, so I can just copy one of these. And this hooks up to my device tree-based STM32 GPIO driver, which I can reuse anywhere I want because I have written it to support the device tree. So let's call this the STM32 GPIO. And then I'll program the pins. So let's have a look here. I have the board here, and I'm going to program the range 1 chip enable. No, that was actually in the wrong window. Range 1 chip enable. Let's have a look where it ends up being here. PB12, PB13, and PB0 and 1. And defaults, so this driver also supports defaults. They're going to be 0 on all of the pins. And I'm actually going to make the pins open drain. So we're just going to be pulling them low. So the pins have, the way that I've designed this, maybe this is the wrong design, because I haven't tested this board yet in terms of the sensors. But the way that I've designed this is that I basically pull this pin low through the pins there. I wonder why I placed it. I wonder why I placed a diode there. But I guess there was some reason I did this. This was a while ago. So let's have a look if we can actually communicate with one of these sensors. So defaults are set. Now I'm going to set up an I2C port here. So I'm going to create an I2C device. This also fits. This is also going to be handled by my I2C driver that supports the device tree, so I can just reconfigure it for any board. Let's see, compatible. It is STM32 I2C, and let's see. Baud is going to be, let's run it 100 to begin with, and then I'm going to create all the sensors here. So we'll have range 1, compatible, and this is going to be handled now by this VL driver. So it's going to have a compatible string that looks just like the text you can see there in device driver definition. So firmware VL6180, and let's see, I2C is going to be, let's see here. I think that I have two of them on one I2C bus. So I have I2C-B and I2C-A. And let's see where this connects. I2C-A. I2C1 and 2. Yeah. So I2C-A is actually I2C2. Let's see here. So this will reference then I2C1, GPIO will reference the range C GPIO, and C pin will be, let's see, we gotta be careful here so that we have the C pins correct. So I2C1 is the I2CB, so it's gonna be range 1 and range 3. So I'm going to use 0 and copy this. Range 3. And this will use the C pin number 2. Now, for the other two, I'm just going to copy this section and just reconfigure the pins. So they're going to be called range 2 and range 4. And this one I'm going to use number 1 and number 3. And they're also going to point to I2C2. So now when we're going to boot the board, we're actually going to see the initialization in the console here. This is the console connected to the board. So as the firmware boots, it will actually output diagnostic messages. And I want to also try to read this version register here. So I'm going to do like this. I'm going to do I2C transfer. Let's see. Just going to check this. So we're going to transfer to south I2C, south address Let's actually specify the address in the device tree, so I'm going to do like this. So first of all, we're going to communicate with the chip using the default address. So it's going to be VL6180 default address. And we're going to write the buffer. Yeah, so the idea is, I think, I'm going to configure the addresses through the device tree. And I will then assign them as I initialize each device. But for now, I don't need to actually worry about the addresses. I just need to make sure that I can at least communicate with the devices. So first of all, this is going to go low. So GPIO set. Actually, I'm going to check if this needs to go low or high. Let's see, where is this? So GPIO 0 is shut down, which could probably mean that, let's see, that if it is high, then it's actually in shutdown mode, I would guess. Let's see. So what exactly is this shutdown? Oh, here we go. Power up timing. So GPIO 0 needs to go to high level, so it needs to start with a low level, then go to high level. Are you fucking kidding me? Is this supposed to be, or maybe GPI 1 is actually the like a default output. Let's see what GPI 1 does. Okay. Okay. So then let's read the registers here. And by the way, I also want to check the structure of the packet that we're supposed to send to it. Device address, index, or index, and then data. Okay, cool. Read does a repeat start. So, let's see here. So then I could just define all the registers here. Let's make sure that all the texts are aligned. This will be 0. Reg model ID. Reg model rev major, minor, and so 5 is actually missing. So this one will be 6, 7, 8, damn it. 0, 1, 2, 3, 4, 6, 7, 8, and 9. Is this somehow like a timer? Time high and time low? Yeah. Okay, so we set the GPIO sub-CE pin, and then we read this register then. So that's enough for now. If model not their default model, see. I'm gonna just print it out like this for now. We'll see what the values look like. So real major mod major mod minor date high and date low and break, then default. I want to just write it like this so that I can just put the semicolon afterwards. Actually, it's probably okay to place semicolon here. It just complains if the semicolon is like outside of any method. Okay. Let's see if this builds. And actually, I'm going to also do this. Try to do this and build it. This is probably going to complain about many things. Actually, I also forgot to add the file to the compilation. course. For some reason, Vim changes the directory there. I have to check if there is some old history somewhere that makes it change the directory. Probably something with the build scripts, because I just copied the build scripts from the other project. Let's see. So, range reference to non-existent label. Range CGPI. Oh. Let's add a few more include files here. C and GPI. And try again. Interesting. Let's return minus one for now. Oh, of course. I modified the wrong file, because the file gets copied to staging there. So let's see here, driver. And let's add this arrow here. Damn, I really need to fix this. Let's see. May work, it may not work. I think that it probably won't work. It will probably just there will probably be some fault with the connections on the board, because soldering these sensors wasn't the easiest task in the world. Let's see, C pin. Let's do like this. So we don't have to cast it everywhere we use it. So C pin and yeah, of course, I need to add this function. See, reg is actually 16-bit integer, so it's going to be reg rotated and reg of that. And I'll initialize that one a bit later. So transfer self, I just see self address, which by the way should be set to default address. It should be, no, actually this one will receive. Let's see. So I'll actually set the address here. And then I'll have to set it after I do the initialization. I'll have to actually read the address from the device tree and then set it to the new address. But for now, this is going to read from the default address. Or actually, interesting. So if I bring that pin low, I wonder if it will actually reset the chip, or if the chip is actually going to be in standby. I wonder if it keeps the register values. We'll have to check that. So I2C transfer. For now, I'm just gonna let's see. Yeah. So actually, I'm gonna make this into a method. So VL6180 begin and let's see. 6180 and the reason for this is because I have to take care of the timeouts. So static and VL6180 begin. Let's see. Let's sleep 1 millisecond and then and I'll just bring this pin to a low value, and then this will also be void, like that. Okay, I'm just finishing this one, so this is going to be TX, RX, TX2 RX 1 and VL6180 I2C timeout. And the value will be, actually this can be read directly into value. Okay. Make this 100 milliseconds. I think that was correct. B4, yeah. Alright. God damn it, where is this happening? Why is it changing directory? This is quite an annoying glitch, because I've been working in that directory before, and now every time I build, it actually goes back to the directory. Highly annoying. Okay, yeah, that's not really necessary. That's actually print default. Actually, yeah, I'm going to use print default, so I can easily change the default colors for this type of messages. Let's see. And it didn't load the driver. Let's see, why didn't it load the driver? Yeah, STM32 I2C needs to be included. I'm just going to add a message that will let me know if some node is if there is no driver for some node. So let's do this. Yeah, this should actually be done here, because otherwise I'll be doing that for every single driver. Very inefficient. So oh, yeah, and this yeah, this gets a little bit tricky for nodes that don't actually have a compatible string. So alright, so it will actually return 0 if there is no compatible element in the tree. So let's see. So if it is more than 0, then we set found true. But if it is 0, then we actually will to check farther. Yeah, this is really ugly. Let's see if more than 0, then we found it. But only if, let's see. Yeah, this gets really messy. So if it is more than 0, then it does have a compatible string and it does have a match, but then we have to make sure that it also probes correctly. And if it is less than 0, can it actually be less than 0? Maybe this one will return less than 0. What does libFdt return here? Okay, so it can actually return less than 0. Okay, I'll have to check this, like exactly what values I get from it. So I'll just print, let's see, missing driver. This is a bit like the way that libFdt API sometimes work is a bit confusing. So this will return 0, return 1. So this will return 1 if, okay. So if it is compatible, then it returns 1. Okay. This is probably completely wrong. But what I do need to make sure is that I actually include the drivers. Let's see. VL6180, and they are not found for some reason. Hmm. There's something with the ground, I think. Let's see. Just gonna make sure that all the wires are connected. Right, it's probably starting up, but it's not actually getting very far. Let's see what is going on here. Okay. I think that's what is happening actually here is that I'm gonna just lower the frequency with which I'm running this for now. Let's see. Oh. Because I think that the main task is actually taking too long, so it actually consumes all of the CPU power. This shouldn't matter actually. It was running at 10 millisecond interval. So what is going on? Is there anything else that... Let me check that. Let's see. Right now I feel that my whole build process is kind of breaking down one thing at a time. In addition to that, my computer is very slow right now. I have around 250% CPU usage. Chrome being high on the list, as always. It's time to close Chrome. I'm not getting anything here. I'm supposed to have all the drivers. Something is completely breaking down. Is the regulator still running? Yep. Did it start or did it panic somewhere? Let's see. I think that I messed it up in the code that actually loads the device tree. Let's see. I think I messed this code up. So check compatible is going to return -1 or 0 if it's compatible. So like, yeah. More or equals 0. Actually, I think it just returns 0 if it is compatible. Otherwise, it will return something negative. So let's do like this for now. So what exactly is going on here? Why is it failing? One thing I'm going to just try here in case something didn't compile properly. Still nothing. Damn it. I messed something up. Something is messed up here. I totally messed something up. And I don't know what. Damn it. What did I do? What did I do? The software is running, but it's not actually programming the drivers. Yeah. Let's try this. Okay, I went past it. But let's see. Interesting. So now it's actually running. What the hell is going on? It is actually running. This is extremely weird. I wonder if it has something to do with the fact that this is like an STM32F. Which one is it? It's like it's F413. This is the only F413 that I use. What the hell is going on? Suddenly it just started running when I connected to it using GDB. If I close this and I restart it, it just runs. Okay, fair enough. Let's see. Unsupported device. Oh, of course. What I forgot here was I forgot to specify the I2C device. Let's see, I2C. I2C1 and I2C2. Let's try this again. Now it's booting. I have no idea why. Let's see. So I2C is initialized, but I cannot communicate with the chip. So can I? Let me check with the scope. Could be something to do with the level conversion, or it could have something to do with the chip select or chip enable. I'm going to check R19. Let's see, R19 is there, and it is supposed to... this one is high, and if I... see what happens if I start the chip. So it kind of gets pulled low, but it could be that maybe this one is not really pulled low properly. It's not actually going all the way down because there is a diode here. Why the hell did I place the diode there? What was my thinking when I placed the diode there? This is supposed to be SDA. SCL is high. SDA is kind of floating, I think. It doesn't look entirely correct. Why did I place this resistor there? I'm gonna check the data sheet. Let's see. No data sheet. This one. VC9306. Let's see. Holy fuck. Like, how could I do this kind of crap? I actually connected the VRF1, which is supposed to be the low voltage reference supply. Connected that to the 3v3, when in fact this one was supposed to be connected to 2.5 volts. Whereas this one is not even connected anywhere. Damn it. What is this crap? This is a total fail. This is what I get when I don't review a schematic properly. How can I fix this? I'm gonna check. Is there like a? No, this is the only table. Okay. So. Like if this was at least connected to 3.3 volts, and if this one was connected to 3.3 volts, then it will be fine. And I can just remove this resistor, but this is connected entirely wrong. Damn it. This board is not going to have distance sensing. This board is fucked. This is gonna have an IMU and CAN bus. I could like use it as a CAN bus IMU or something. Yeah. Alright. Blinking the LED. Look. Damn it. Okay, I'm done for today. And thanks for watching, and I hope you learned that reviewing the schematics is probably the most important part of designing them.